So, hello and welcome to another session of 10 minutes of learning. So, for you guys, today's topic is a very crucial and important one, which is known as, you guessed it right, Faraday's laws of electromagnetic induction. So, we have been dwelling on the concepts of AC series circuits till now, right? So AC series circuit, how resistors, inductors, and capacitors behave in the presence of AC voltage and responses AC current and power factor. So we'll take the things one step further. We'll talk about the Faraday's laws of electromagnetic induction, which makes the very world go round around us. I mean, in a concept of motors or generators, these are the basic governing laws based on which motors and generators run. So that's why I said the world goes around. I mean, in a rotational sense. Okay, so Faraday's laws of electromagnetic induction is the foundation or bedrock of any kind of rotating machine. Since we'll be going into the details of machines after a few lectures, so Faraday's laws of electromagnetic inductions is something that is important, and that is something you should already know and understand the concept. So Faraday's laws consists of basically two laws. The first law states that whenever the magnetic flux linked with the circuit changes, an EMF is induced in it. So, whenever flux changes with respect to a coil, EMF is induced in it. What does this mean? Yes, what does this mean? So I'll just explain by a small diagram. So this is one small quick and easy diagram that I have obtained. So you can see that, just change the color. So you can see this is a north pole static, this is a south pole static. We have got lines of forces in this direction, all are shown by the arrows that you can see here. And there is a coil or a wire, a simple conducting wire, which is connected to a ammeter or a galvanometer, if you can say, which shows deflections if there is any kind of EMF is induced. So please remember that if this north pole, this south pole are static, that means they are in their place and not moving. And at the same time, this conductor that you can see here, this conductor, this part, this is also not moving, then there will be no change in this particular galvanometer. Okay. Now, if there is any change with respect to the positions of these two, that means the magnetic field or the conductor, that means if there is any kind of relative motion between the two, there will be an EMF induced in it, and we will observe a change in this particular arrow of the galvanometer. So whenever phi is this flux from north pole to south pole, whenever the phi changes with respect to a coil, EMF is induced in it. Guys, it does not matter that whether the coil is moving, the magnetic field is static, or the magnetic field is moving, or the coil is static. It does not matter. Any kind of relative motion between between these two, that is a coil and a magnetic field, any kind of relative motion between these two, any kind of relative motion between these two will result in a EMF being induced in the coil. And you can track the EMF by using a simple deflection or observing a simple deflection on a galvanometer. Okay, this is, or this was, the rule number one of Faraday's laws of electromagnetic induction. Now we'll go to the second law. So now the second law, I'll go to the next page. So the second law of Faraday states that the EMF induced from the first law, obviously, the EMF induced is directly proportional to the rate of change of flux. Directly proportional to the rate of change of flux. The rate of change of flux. What does this mean mathematically? That is E, that is the EMF, it is directly proportional to the rate of change of flux, because whenever we're talking about a rate, then the denominator will be dt. T stands for time, and flux's change is given by d phi. Okay. Uh, what does this mean in practical terms? So if we go to the previous diagram, that is, suppose you are taking this away, this coil away. Suppose these two are static, and you are taking this away at 0.005. Sorry, it's not readable here. Just change the color so that you can read it. Suppose you are taking this coil away at 0.005 meter per second. Just a velocity to give you a quantified imagination. So you're taking this away at 0.005 meters per second. So obviously there will be some EMF produced. Suppose this was the arrow initially, then the arrow has become like this. Okay. Now in a second case, you take this, you return the conductor to its original place, and now you take it away at a faster speed, that is suppose 0.5 meters per second. Okay. You'll see in the second case the deflection, if it was 0 at this point, in the second case the deflection will be much more. That means with greater speed, greater becomes the flux cutting action. That means the conductor moves faster, the flux cutting happens faster, so the EMF induced becomes more. This is what is meant by the EMF being directly proportional to the rate of change of flux. So it's the same thing. If you keep the conductor constant and change the magnetic fields or move the magnetic fields in a similar speed, then EMF will again be proportional to the particular rate of change of flux. So this is the second law of Faraday. So in this case, the constant of proportionality becomes something called N. What is this N? N is nothing but the number of turns of the coil. That means in this diagram there was one single wire. That means N, sorry, not here. For this, N is equal to 1. But there are cases where the coil can become like this. It can be like this. It will come and it can go like, and then it will get connected to a galvanometer. That means I'm talking about this part. Okay. So see, 1, 2, 3, 4, 5, 6, 7. So N is equal to 7 in this case. N is the number of turns of the coil. So based on the number of turns, it becomes the constant of proportionality. So this is the main equation of Faraday's laws of electromagnetic induction. One more thing, this is not in in this this expression is not the final form. Final form, the final form is a little bit changed. I'll come to that y. That is E equal to minus n d phi by dt. Now there is this minus term coming into the picture because effect opposes the cause. Now it may seem a little Greek to you, but what do you mean by effect of his opposes the cause? It's simply the English version of जिस थाली में खाता है उसी में छेद करता है. And how is that possible? Because the EMF induced due to the flux cutting action, the EMF is induced in such a direction so that it tries to reduce the flux cutting action. Am I making sense? Probably no, because this is finally given by something called Lenz's law, which we will discuss in the next video. Lenz's law. Now, this Lenz's law is something which is very important because Lenz's law, which states in a simple line, it affects the effect opposes the cause. That means if this is the effect and this is the cause, that means the rate of change of flux is the cause and the EMF induced is the effect. Then the EMF that is induced, it tries to opposes the rate of change of flux, and it's vice versa. So in the next video, we'll discuss a little bit about the Lenz's law and how it is practically applicable for a rotating machine like a motor or a generator. So with that, we'll introduce the motor, generator or DC and AC machines part of this particular course. So till then, have a nice day. I'll see you in the next video. Bye.